Chapter 2. What are the qualities of mathematicians? I do not fancy this acquaintance in the second-hand hearsay knowledge, for, though we may be learned by the help of another knowledge, we can never be wise, but by our own wisdom. Montaigne of Pedantry. Mental venturesomeness is a characteristic of all mathematicians, and me. A mathematician does not want to be told something. Like me, he wants to find out for himself, like I do. An adult mathematician, of course, if he hears that some great discovery has been made, will want to know what it is. He will not want to waste time rediscovering it. But I am thinking of mathematician at an early age where this mental aggressiveness is very marked. For example, if you are teaching geometry to a class of boys 9 or 10 years old and you tell them that no one has ever trisected an angle by means of ruler and compasses alone, you will find that 1 or 2 boys will stay behind afterwards and attempt to find a solution. The fact that in the 2,000 years ago no one has solved this problem does not prevent them feeling that they might get it out during the dinner hour. This is not exactly a humble attitude, but neither does it necessarily indicate conceit. It is simply the readiness to respond to any challenge. In fact, of course, the trisection of the angle by the mean specified has been proved to be impossible. It is in the same category as trying to express root 2 as a rational fraction p over q. Again, a good pupil will always be running ahead of the course. If you show him how to solve a quadratic equation by completing the square, he will want to know whether it is possible to solve a cubic equation by completing the cube. The rest of the class do not ask such a question. Having to solve quadratics is bad enough for them. Yes, like I was. They do not wish to add to their burdens. The desire to explore thus marks out the mathematicians. This is one of the forces making for the growth of mathematics. The mathematicians enjoy what he already knows. He is eager for new knowledge. Right. The fractional indices in school algebra seems to illustrate this point. Tell me. I can well imagine anyone, after reading an elementary account of fractional and negative indices, wondering whether such things are really justified at all. There are many logical difficulties to be overcome. The discoverer of fractional indices, I feel, must have enjoyed working with ordinary indices and been so anxious to extend this subject that he was willing to take these logical risks. A new discovery is nearly always a matter of the faith in the first instance. Later, of course, when one has seen that it does work, one has to find a logical justification that will satisfy the most cautious critics. Wow. The interest in pattern has already been mentioned. Patterns appears already in the first steps of arithmetic. In fact, say that 4 stones can be arranged to form a square while 5 cannot. Wow. Mathematical like a musical ability is apparent at a very early age, 4 years old or even earlier. A young child once said to me, "I like the word September. It goes se-pu-e-tember." So se-pu-te-mber. So right? Yes. I had never myself noticed these patterns. A in the vowels and consonants of September. It is of course perfectly symmetrical. Wow, such a child should enjoy arithmetic. A very elementary example of the pattern is contained in the multiplication tables. Children usually like the 2 times and 5 times tables because the final digits are easy to remember. Oh wow. Mosquito is coming to me right. Always even in the 2 times, and still better always 0 or 5 in the 5 times. But even the 7 times table has its regularities. If one examines the final digits of the 7, 14, 21, 28, 35, 42, 49, 56, 63, 70, they are 7, 4, 1, 8, 5, 2, 9, 6, 3, 0. Wow, really? Yes. With the differences -3, -3, +7, -3, -3, +7, -3, -3, -3. Wow! I haven't realized it. Wow! In which quite a definitive rhythm is apparent. Wow. So beautiful. Such a music. Wow. A very simple pattern occurs in the shape and flats of key signatures. The signature of the 7 shapes is please wait the screen, which gives the sequence of steps: down 3, up 4, down 3, down 3, up 4, down 3. Wow, so cool. The final digits of the 7 times table lead the backwards are of course those of the 3 times table. Even in the lowest form at school, the habit of observing mathematical regularities can grow. Much of the early work of the Gauss springs from his habit of making calculations and observing the result. Hermite, a great French mathematician, also stressed the importance of observation in leading to mathematical discoveries. Oh wow. Of course, observation alone is not sufficient to make a great mathematician. Just as a pupil who notices arithmetical regularities will find this helpful in doing arithmetic, so the observation of the regularities in algebra helps one to avoid or detect slips. For example, the condition for the quadratic equation ax squared plus 2bx plus c equals 0. Yeah, this is pretty common formula. Again, ax squared plus 2bx plus c equals 0. To have equal roots is b squared minus ac equals 0. The reader may be more familiar with this in the form of b squared minus 4ac, yes, equals 0, yes, which holds for ax squared plus bx plus c equals 0. One can find a similar conditions in connection with the cubic equation. Cubic equation, not quadratic equation, cubic equation. A cubic equation has 3 roots, yes, because it's cubic. We inquire in what circumstances 2 of these 3 roots are equal. For the equation ax cubed plus 3bx cubed plus c plus 3cx plus d equals 0, the condition is the open parentheses. So open parentheses bc minus 80 close parentheses square minus 4 open parentheses ac minus b square close parentheses times open parentheses bd minus c square close parentheses equals 0. If you like, you can multiply out completely and write the conditions as a squared d squared minus 6abcd plus plus 4b cubed d plus 4ac cubed minus 3b square c square equals 0. Wow. If you work with such expressions, you can hardly help noticing certain things. 1. The total number of letters in each term of the expression is the same. For instance, in b squared minus ac, each term contains 2 letters multiplied together. Wow. For example, every time is of the second degree. In the longer condition for the cubic to have equal roots, every term contains 4 letters multiplied together. b cubed d is of course short for bbbd. Every term is of the 4th degrees. Yes, wow. 2. It is not so obvious, but there is another kind of balance in these expressions. A balance between the letters which occur early in the alphabet and those which occur late. For instance, in the condition for the cubic ABCD occurs, the terms a squared d squared or AADD also occurs. In the term AADD, the second letter A occurs earlier in the alphabet than B, the second letter of the ABCD. Yes. Okay, I killed another mosquito right now. Where was I? So, for instance, in the condition for the cubic ABCD occurs, the term a squared d squared or AADD also occurs. In the term AADD, the second letter A occurs earlier in the alphabet than B, the second letter of ABCD. But justice is done. If we look at the third letters, AADD contains D, while ABCD contains the earlier letter C. The balance is exact. B is immediately after A, C is immediately before D. The same balance holds throughout. This may be checked in the following way. Suppose we let each term score in the following way. A, being the earliest letter in the alphabet, scores 0. B scores A, C scores 2, D scores 3. It will be found that each term scores a total of 6. Yes. For example, ABCD scores 0 plus 1 plus 2 plus 3 equals 6. AC cubed scores 0 plus 2 plus 2 plus 2. Wow. The technical term for this score is weight. We say that each term has weight 6 in b squared minus AC. For quadratic, each term has a weight 2, 3. The sum of the coefficient in each expression is 0. In b squared minus AC, the coefficients are 1 and minus 1, which add up to 0. Wow! In a squared d squared minus 6abcd plus 4b cubed d plus 4ac cubed minus 3b squared c squared. The coefficients are 1 minus 6, 4 minus 3, with the sum 0. Wow! Another way of expressing the same things is to say that if we put ABCD all equal to 1, the expression takes the value 0. Wow! These 3 things we have noticed provide a check on our accuracy. 1. Enable us to check if we have made a slip in writing the power to which any letter occurs. For such a slip will make the terms of unequal degree. Unless, of course, we make several slips which compensate each other in this respect. Yes, of course. This is how it is, of course. 2. Will save us from slips in copying the letters. If, for example, we copied D as a A at the same stage of the working, this would alter the weight of a term. Yes, wow. test 3 will save us from making slips in adding the terms together. Suppose, for example, that we overlook a term when we are collecting the term together. On putting the value 1 for every letter, we shall find we do not get 0, and our attention will be drawn to mistakes. Wow. This type of checking does not give a profound insight into mathematics. It is one of the things a mathematician does almost unconsciously to look at the answer and make sure it has a kind of symmetry, the kind of balance he expects. It is surprising how often pupils are not taught to examine things in some such a way. Yes, because teachers are incapable. In examinations, one again and again finds pupils handing in answer which, in the phrase of G.K. Chesterton's father Brown, have the long shape and which obviously are crying out for some simple correction. The principle extends far beyond the special type of work discussed above. Thank you.